Dear students, welcome to this module and let us continue our study of this paper Organic Chemistry 4, that is Advanced Organic Synthesis and Supramolecular Chemistry and Carbocyclic Rings. In this particular module, we shall continue our study on the disconnection approach and we shall be dealing with the synthons, synthetic equivalents and the retrosynthetic analysis. After studying this module, you shall be able to know about what is this term synthon all about. You shall be able to know about the synthetic equivalents and study the steps involved in retrosynthetic analysis. We will take some examples and you shall be able to know the routine for designing the synthesis. You are already aware that organic chemistry is a branch of chemistry which deals with the study of carbon and its compounds. And this study includes the understanding of the synthesis, structure, properties and reactions of organic compounds. The organic synthesis is an inseparable part of organic chemistry and is involved in the construction of organic compounds using different types of appropriate organic reactions. To understand an organic reaction, it is essential that its reaction mechanism is completely explored. When we study a reaction mechanism of any chemical reaction, we find the involvement of so many chemical species taking part directly or indirectly along with the movement of ions, species, electrons, atoms and so on. And many reactions you have already studied. But then if you have to design that given a molecule, how to construct and design a synthesis, that is what is the disconnection approach. So, moving towards that, in this module we are going to emphasize on the various species which are involved to build up that bigger molecule. So, we will start with knowing the terms synthons and synthetic equivalents. Synthons are the chemical fragments obtained from the disconnection of bond or bonds of the target molecule. The disconnection of bond or bonds is possible in three ways, and these cleavage you are already aware, that is the homolytic cleavage, heterolytic cleavage or via the concerted transform. What we mean by them? The homolytic cleavage is a process of bond dissociation where each fragment present in the parent compound retains one of the originally bonded electrons, as you can see in this figure. And this type of cleavage leads to the formation of free radical species. Talking about the heterolytic cleavage, the heterolytic cleavage is a process of bond dissociation where both the electrons forming the bond get shifted to one of the fragments present in the parent compound, and this you can clearly see in this particular figure as shown here. And this process leads to the formation of ions, obviously one positive and another negative. So, the part possessing the electrons will be called as an ion and the other deprived one will be called as the cation. Talking about the concerted transform, the concerted transform is a simultaneous or a concerted thing, and this leads to the formation of neutral species, as you can see in this particular figure. This cyclohexene, as these electrons movement take place, they will be resulting in these two fragments, one butadiene and another ethene. So, there is a simultaneous shift of these electrons happening and that is leading to the cleavage of these bonds. Talking about the heterolytic cleavage for disconnection of a carbon-carbon bond in a molecule, this cleavage will break the target molecule into an acceptor synthon, that is a carbocation, and a donor synthon, that is a carbanion. The formation of any carbon-carbon bond involves the union of an electrophilic acceptor synthon and a nucleophilic donor synthon. That is, the acceptor synthon will be acting as the electrophile or the electrophilic species, and the donor synthon will be acting as the nucleophilic species because it is electronically rich and it can donate act as a nucleophile. Knowing about synthons, let us know what are synthetic equivalents. Synthetic equivalents are the chemical species which are used to generate synthons. They are the actual substrates used for the forward reaction and hence the forward synthesis. Also, the synthetic equivalents are the reagents derived from inverting the polarity of the synthons. For example, in the retrosynthesis of 4,4-dimethyl 1-phenyl pentane 1-ol, you can see this structure 1 depicting this molecule. So, for the retrosynthesis of this particular molecule, the synthons and the corresponding synthetic equivalents are as shown. So, you can see here that making this disconnection from this particular bond as shown here, it will be leading to these two synthons, one carbocation, another carbanion. So, these are the synthons. But then what are the real reagents you will be using to have a positive or a negative polarity in the synthons? These are the synthetic equivalents. So, the synthetic equivalents you can see here are these 4 and 5, that is corresponding to second synthon you will use this synthetic equivalent which is benzaldehyde, and corresponding to this third carbanion as synthon you will be using this fifth which is this Grignard reagent, because MgBr being the positive part, they will be corresponding negative generated at the position where in the synthon we require. So, the corresponding reagents are those where they will be giving us those corresponding positive or negative polarities of the synthon. Let us look at this case again. This is very important to make you understand. The cleavage of the compound 1 between C2 and C3, they gave rise to the synthons second and third, and these can be generated from the synthetic equivalents 4 and 5 respectively. The list of the electrophilic acceptor synthons and the nucleophilic donor synthons along with their corresponding synthetic equivalents, let us look in this tabular form. Let us take these particular acceptor synthons first. So, if the acceptor synthon, obviously as I told you earlier, acceptor synthons are electrophilic, they are electron deficient and they are the positively charged carbocation synthons in this. So, if you have R plus, the corresponding synthetic equivalent, that is the reagent that you will be using, will be either RCl or RBI or RI or ROTS. Taking the case of Ar plus, that is aryl cation as synthon, you will be using aryl diazonium salt, because the moment you have this dissociation you will be generating the Ar plus. Looking at this particular case where you have this carbocation, where this can be generated from this particular synthetic equivalent, that is the epoxide. Moving to the next where this is the another carbocation directly attached to OH, then this can be generated from the corresponding carbonyl, that is if you have both the R here, then it will be corresponding, the parent synthetic equivalent will be ketone, but if it is one R and one H along with OH and the positive charge on the carbon, then it can be generated from the aldehyde. Taking another example, if you want to generate this particular synthon, then at this particular position you have a positive charge. So, you can attach a Br here, and being at the alpha position, then this can be taken and given this particular transformation. Then looking at the next case where you have nitrile, and then respective to the nitrile at the beta position you have positive charge on the carbon, then putting a double bond here in the conjugated position to the nitrile, and because of the mesomeric shifting there will be a positive charge coming at this required position. So, you have to keep in mind that how which synthetic equivalent you have to take, so that you get the corresponding positive or negative charge at that very particular carbon. Let us look at the list of some common donor synthons and their synthetic equivalents. If you have R minus, the reagent can be RMgX or RLi or R2CuLi or Rx in the presence of metals, because that is how you will be able to generate the R minus. Talking about Cn minus, yes, it can be HCN, from which easily the Cn minus can be generated. Talking about RC triple bond C minus, the alkynide anion, then this can be generated from the parent alkyne, and again you have guessed it right, from taking the help of sodium ammonia type system, you can remove this proton and generate the corresponding carbon ion at this particular position. Talking about this alpha carbon ion, the next one alpha 2 carbonyl, obviously the synthetic equivalent will be the parent neutral acetone, and similarly if you have the negative charge on the alpha 2 nitro, then the precursor will be the corresponding neutral molecule. So dear student, by giving you this list, this is not the complete list, but we have given you idea that keeping in mind that whether you want the positive or the negative charge on that very particular carbon from where you have done the bond cleavage in the retrosynthetic analysis, you have to think for a synthetic equivalent which will be your actual starting material to combine and do the forward synthesis to get the target molecule. So let us build up more around this concept and try to know what is retrosynthetic analysis. The construction of a synthetic pathway by working backwards from the target molecule is called retrosynthetic analysis, and this helps chemists to design the synthesis on paper, and then you can work up into these pieces and really it can be built up into a bigger molecule. The symbol arrow with two lines, so it is a double arrow, not double sided, single sided, but with two lines. This signifies a reverse synthetic step, and this is called a transform. So when you are writing the forward reaction, you simply write one line with single side arrow, but when you are using two lines and arrow, then this is signifying a reverse synthetic step and called as a transform. In a reverse synthesis or retrosynthetic analysis, we actually move from the target molecules to the synthons and then further to the synthetic equivalents, and this can be represented in this way. So you have the target molecule first, you break the target molecule from different positions, that is how you get different retrosynthetic routes, and then breaking that will be giving rise to synthons which are positively or negatively charged species, and then corresponding to each of these synthons you have to build up or think for synthetic equivalents. And when you really carry out the reaction starting from these synthetic equivalents in the appropriate conditions and reagents, then you mix them and get the target molecule back. So the design of a synthetic pathway for any molecule needs to take into account some of the important aspects, and what are these? These are the methodology actually should work in the experimental condition. In general, the number of synthetic steps must be as less as possible. The yield of each step must be good to excellent, because the more the number of steps, the overall yield will be less if the yield in every step is less. The side products and impurities must be easily separable from the desired product. The synthetic steps must follow the principle of green chemistry. The synthetic process must be economically viable. So when we apply disconnection approach or the retrosynthetic analysis for any target molecule, we must take into account all these aspects, and then and only then it will be more commercially viable synthesis that you have evolved or designed. Let us also talk about the strategy in retrosynthesis. For making the strategy in retrosynthesis, different possibilities have to be worked out. We can try a number of disconnection and functional group interconversions, which we have already studied, based on the knowledge of the basic organic chemistry. So I will advise you that you should revise your named reactions and dealing with whatever type of retrosynthesis, what functional group you are dealing, just revise the forward reactions that you have studied, because that is how you will be able to know the backward reaction, from where to break the molecule and how to go about. Let us move further now. There are actually two types of routes possible. One is called as the convergent route and the other is called as the linear route. A comparative pathway for both the routes you can see here in this particular figure, and in order to understand both of these routes, let us consider a compound ABCD and see how the possible disconnection approach for this molecule are there. In the convergent route, as you can see, ABCD molecule is being broken from in between, that is between B and C, and as a result you are getting the fragment AB and CD. Further, AB is broken into A and B and CD is broken into C and D, and that is how you are getting these corresponding synthons and further the synthetic equivalents. On the other hand, if you look at the linear route for the same molecule for the retrosynthetic analysis, then linear route is going, as the name suggests, in one line. It is starting from one end of the molecule and going towards the other end. That is, first of all, we are breaking between C and D, which is the extreme end. As a result, we get A, B, C and D. Further, we target on ABC, break it between B and C, and we get AB and C, and then we target on AB, break it further and go into A plus B. So, as a result we get A, B, C, D fragment in both of them, but now you can see in the convergent route the molecule is broken randomly from in between, but in a linear route it is from one side. Out of these two routes, the convergent route has been found to be better than the linear one with respect to the overall yield. So, hence for the disconnection of any molecule, we must keep in mind the following rules for simplification, that is, target somewhere middle of the molecule, that is where you should try to break the molecule from. And then you can also adapt this approach, that is, disconnect at the branch points or look for the bond which makes the symmetry of the molecule. And let us take one example in each of these. For example, the cleavage in the middle of the molecule, you can see here in this particular molecule. Here when we are breaking, we are targeting right at the middle of the molecule, and that is how we are getting the corresponding synthons for which we can look for the synthetic equivalents. The next example you can see here, we are targeting on the branching. So, you can see this is the branch and this is being broken, and that is how you are getting the corresponding synthons. The next figure, we are actually focusing on disconnection at the symmetry point. You can see this being a symmetrical molecule at this double bond. If we are trying to break this molecule, we can look for a precursor alcohol which can be easily dehydrated to this alkene, and then in this particular alcohol at this symmetry point, again we are trying to break it and we are getting the corresponding synthons for which we can look at the synthetic equivalents. So, dear students, this module has given you idea about the term synthons, the synthetic equivalents, and how to go about the disconnection approach. And before we move to the next module, let us summarize what we have learnt in this particular module. We have learned that the organic synthesis is an inseparable part of organic chemistry and is involved in the construction of organic compounds using different types of appropriate organic reactions. But in order to build this, we have to be knowledgeable about disconnection approach. We studied about synthons. Synthons are the chemical fragments obtained from the disconnection of bonds of the target molecule. The disconnection of bonds is possible in either homolytic cleavage manner or heterolytic cleavage or via the concerted transform. We also studied about synthetic equivalents, and let me tell you again that the synthetic equivalents are the chemical species which are used to generate synthons. They are the actual substrates used for the forward reaction and hence are utilized in the forward synthesis. The construction of a synthetic pathway by working backward from the target molecule is what is called as retrosynthetic analysis. The design of a synthetic pathway for any molecule needs to take into account some of the important aspects that we have discussed in detail. So, I am sure that you have to keep all these things in mind and then you will be able to understand the further topics that we will be taking in this retrosynthetic analysis.